Hello and welcome to a new lecture on the binomial theorem. In this lecture we will look at several example problems based on the binomial theorem which you may face in an exam type situation. So let's recall the binomial theorem once again, which is nothing but x plus y the whole power n equals summation r equal to 0 to n cr x power n minus r y power r, where cr is used to denote ncr. So far we've seen several results which can be derived from the binomial theorem, but most of the results we've seen have been subjective kind of questions. We haven't really seen many objective problems which you may face in an entrance exam, and so in this lecture and in the next one we will look to fill that void, and we will present a few examples where you have objective questions which may appear in an exam. So note that we are not trying to exhaustively cover all kinds of examples in these lectures. For that I refer you to your supplementary textbooks which you may be using to prepare for the exam. So let's see a first example. The question is c0 over 2 minus c1 over 3 plus c2 over 4 and so on until minus 1 power n plus 1 cn plus 1 over n plus 3 equals, and the options are 1 over n plus 1, 1 over n plus 2, 1 over n times n plus 1, and D, none of these. So whenever you're faced with such a question in an exam situation, your first impulse might be to try out certain values of n to try and narrow down on the final answer. And in cases where you have when you have an option which says none of these, that might not be that might not yield a satisfying result, since you might not be able to determine which one of these, whether one of these options is the right answer or whether none of these is the right answer. So to be safe, it is best to actually derive the result for this problem and then finally narrow down on an option rather than just plugging in values of n. However, my advice is to first try out a few values of n to sort of bias your intuition towards one of these results, and then to rigorously show that that is true. In some cases, you might be able to show that one of these answers is the right answer just by plugging in a few well-chosen values of n. So let's see how this may be derived. So let's write the summation as summation r equal to 0 to n plus 1 minus 1 power r cr over r plus 2. So this is the summation we have in this example, and notice that the summation looks quite similar to the examples we've seen in our previous lectures, where we have a fractional term dividing binomial coefficients and you have minus 1 power r. So to arrive at this result, we can look at the binomial expansion of 1 minus x the whole power n. This is nothing but summation r equal to 0 to, let's look at expansion of 1 minus x whole power n plus 1, since we have n plus 1 here. This is summation r equal to 0 to n plus 1 minus 1 power r n plus 1 cr over n plus 1 cr times x power r. So this is the binomial expansion of 1 minus x the whole power n. Notice that this summation is requiring you to divide by a fraction r plus 2. So since we only have x power r, integrating this equality will only give us a denominator of r plus 1, but we want a denominator of r plus 2. So one way to artificially induce a denominator of r plus 2 is to multiply both of these sides by x. So you multiply both the left hand side and the right hand side by x, and you can then integrate both of these sides from x is 0 to x is 1. So this trick is the trick here is to multiply by a suitable power of x so that you can derive a suitable denominator when you integrate these expressions. And the integrating part is very similar to some of the examples we've seen in the previous lectures. So you can do this, and you can go through the math. I'm not going to derive this result, but essentially you can expand these, and you notice that the right hand side is just going to be nothing but summation r equal to 0 to n plus 1 minus 1 power r n plus 1 cr x power r plus 2 over r plus 1, and this is just going to be between 0 and 1. So you notice that this right hand side gives you exactly the summation that you seek. And so if you evaluate the integral on the left hand side of this expression, you're going to land up with the answer you desire. So you can compute this integral using standard techniques. I'm not going to do it in this case, and you will see that the answer actually is none of these. So this answer could have also been achieved by plugging in suitable values of n. So for instance, you can plug in n equal to 2, which will distinguish between these three results for sure, because here you would have 1 by 3, here you would have 1 by 4, and here you would have 1 by 6. So the answer, if the answer is none of these three answers, then you can conclude that the answer is none of these, and that will be true if you work this problem out. So I leave this as an exercise to the viewer. So in this lecture and in the next lecture, I'll only be going over the overview of the solution techniques, since we've already seen many problems of these natures in our previous lectures. And let's look at a second example now. So this asks you to evaluate the value of 47C4 plus summation r equal to 1 to 5, 52 minus r C3. And the options are 52C4, 51C3, 51C4, and none of these. So once again, there is an option which is none of these, and in any case, it seems quite hard to brute force this answer. So since you have many pretty big binomial coefficients here in this expression, it seems hard to arrive at a result just by working the answer out numerically. So let's look at a systematic technique by which we can attack this problem. So the first thing you can do is notice that there seems to be nothing special about the summation, since the summation just seems like a shorthand for writing out 5 different terms. So let's actually expand the summation and see what we get. So we have 47C4 plus, for r equal to 1, we have 51C3. Next term is 50C3. We have 49C3. We have 48C3. And we have 47C3. Written in this way, there doesn't seem to be anything special about this summation. But notice that there are 2 terms which involve the number 47. So if we can somehow collapse all these terms into a single term, then we would get one of these answers. Otherwise, it could also be none of these. So recall that we've seen the identity NCR plus NCR minus 1 equals n plus 1 CR. We've seen this identity in our very first lecture. So let's see if we can use this identity somehow. So there's a 47C4, there's a 47C3. So with n is 47 and r as 4, we can combine these 2 terms into a single term. And the good thing about this is there is sort of a domino effect. These 2 terms collapse into a 48C4, and then there's a 48C4 and a 48C3, and those two terms collapse and so on. So there seems to be a nice pattern which you can employ to get at the result. So let's rewrite this. Let's move the 47C4 all the way to the end, and we have 51C3 plus 50C3 plus 49C3 plus 48C3 plus 47C3 plus 47C4. So we are going to combine these two terms to get 48C4, and then this becomes 51C3 plus 50C3 plus 49C3 plus 48C3 plus 48C4. And you can combine these two terms using the same trick once again to get 49C4 and so on, and you would expect to get 51C3 plus 51C4 the same as 52C4, and that is option A. So here we've seen a nice application of the identity NCR plus NCR minus 1 equals n plus 1 CR to collapse several binomial coefficients in a summation to a single binomial coefficient. And so this is a very nice example in that regard. So to see if you've grasped this concept of rewriting the terms so that you can collapse them in this form, let's look at this following example. It asks you to compute the value of summation r equal to 0 to m n plus r c n. The options are n plus 2 c n, n plus m plus 1 c n, n plus m plus 3. Sorry, the second option is Cn plus 1. Third option is n plus m plus 3, Cn plus 1. The last option is n plus m plus 1, Cn minus 1. So these are the four options which are given to you. So again, for this example, it is probably possible for you to plug in suitable values of m and n into this expression and derive and narrow it down to one of these four options if you are choosing m and n in a clever manner. But where's the fun in that? Let's try and derive what the answer actually is. So let's see what this summation actually looks like. So for r is 0, you have NCN. For r is 1, you have n plus 1 Cn. R is 2, you have n plus 2 Cn, and so on till n plus m Cn. So this is the summation which you're given in the problem. So at first sight, there doesn't seem like a way in which you can use this identity, since all of the terms in the bottom row all seem to be n, whereas this identity requires that they differ by 1. So it doesn't seem like there is a way you can use that identity, but there actually is by using a suitable transformation. So you notice that we can use the fact that NCR is the same as NCN minus R. So you can rewrite this as NC0 plus n plus 1 C1 plus n plus 2 C2 and so on till n plus m Cm. So using this trick, we see that the numbers in the bottom half seem to be varying by 1, which is what we wanted before we applied this trick. But we still don't see NCR and NCR minus 1 anywhere in this expression. So that's kind of sad. But there is a way to artificially induce it. So notice that NC0 is the same as n plus 1 C0. So you can write this as n plus 1 C0, and this is n plus 1 C1. So now we have introduced this form NCR plus NCR minus 1 is n plus which can be written as n plus 1 CR, and you have this domino effect all over again. So I'm going to leave the computation to the viewer. So you have this domino effect going, and your final result should be n plus 1 Cm. So once you derive the final result, you notice that none of these options seem to match. But once again, you can use NCR is the same as NCn minus r, and rewrite this as n plus 1 C n plus 1, which agrees with option B. So the final result is option B. So once again, we've seen yet another application of the identity NCR plus NCR minus 1 is n plus 1 CR. So this should give you sufficient numerical experience towards solving such kinds of problems. Now let's look at a fourth example which you may face in an exam. So this example asks you to evaluate summation r equal to 0 to n, summation s equal to 0 to n, r plus s, NCR, NCS. And the four options you're given are 2 power 2n, n times 2 power 2n, n times 2 power n, and none of these. So once again, you might be able to narrow down your options based on suitable values of n in this expression. But since there is none of these, you can't really be sure that one of those options is the right answer. So let's try and derive what this answer actually is. So let's see. We have summation r equal to 0 to n, summation s equal to 0 to n, r plus s, CR, CS. So this is the given expression. Now you can expand this expression as summation r equal to 0 to n, summation s equal to 0 to n, and you have r times CR times CS plus s times CR times CS. So these are the two terms in your expression now, and you have the summation. So notice that you can rewrite these summations as summation r equal to 0 to n RCR times summation s equal to 0 to n CS plus summation r equal to 0 to n CR times summation s equal to 0 to n SCS. So I've just distributed the sum across the summation, and you get these two results. And notice that I've separated the summations over r and s since they're independent variables in this example. So notice that these two terms look very similar. There's just a change of variables, so r is renamed to s and s is renamed to r in the second term as opposed to the first term. So this is nothing but 2 times summation r equal to 0 to n RCR times summation s equal to 0 to n times CS. So I've just noticed that these two terms evaluate to the same value. I've just replaced this whole expression by 2 times the first term. So in our previous lectures, we've derived that summation RCR r equal to 0 to n is n times 2 power n minus 1. So I refer you to our previous lectures where we've derived this fact. Also, we know that the summation of the binomial coefficient is 2 power n. This has also been derived in a previous lecture. So when you put these all together, you get n times 2 power 2n, which is option B. So the right result is option B. So once again, you could have distinguished between these options by looking at a value of, say, n equal to 2. You could have distinguished between these 3 options. but you wouldn't really be sure whether the answer was B or D in such a situation. So it's in cases where you have an option which is none of these, it is best to actually derive the result to verify that you have the right answer. So again, we've seen an application of the previous examples we've seen in this lecture series, and that's all for this lecture. I hope you enjoyed watching this lecture, and thank you for your attention.